Should I start or?
Yeah, we can start now.
Yeah,
Yeah,
please begin, Bhumika.
yeah, sure. Okay.
So, good afternoon, everyone. So, I'd like to extend a warm welcome to all of you for today's talk. This talk is organized by Curry Leaf, MTTS Alumni Club, in association, in collaboration with MTTS Trust. So, today we have with us Dr. Pradip Kumar. A warm welcome to you, sir. So, Dr. Pradip Kumar is always, he is
Bhumika,
associated with so
your voice is not clear. Can you please increase the volume?
Oh, okay, okay.
Bhumika,
Um,
your voice is not clear. Can you please increase the volume?
is it clear now?
It is better, but yeah, still. So
I think now it should be
now it's clear. Yeah.
great. So, yeah, so I was telling that Dr. Pradip Kumar is associated with so much of esteemed institutions. He's currently working in Shiv Nadar University, Noida. He did his PhD in HRI and then he did his MSc in IIT Kanpur. Besides that, one proud moment to all of us is he's an MTTS alumni. His research interest include differential geometry, complex geometry, and algebraic geometry. So today he's going to tell us about minimal surfaces. So when I read his abstract, although I didn't understand much, but it sounded a lot interesting. So over to you, sir.
Thank you, Bhumika, for such a nice welcome. Uh, Before I start minimal surfaces and before I start mathematics, I just want to say something. So actually, I always feel a deep connection whenever anything related to MTTS comes up. So I just want to say something. Uh, so I attended my first MTTS camp in summer 2008 at RI Mysore, and long back. So, but I still remember many things that happened there, and that changed my perception how to think mathematics. I was little privileged because I was a MSc student in IIT Kanpur. So I was little privileged having Professor Santhanam as my teacher in IIT Kanpur. So I got a little bit glimpse how to think and pursue some mathematical content. In this via this platform, I just want to thank uh, every one of you related associated with MTTS. Actually, words are not enough to express my gratitude for for the dedication and the teaching method that had a lasting impact, not just on me, but you all can relate on generations also. And then how can we forget the famous curry leaf trick? Every one of us can remember all. I encountered the curry leaf trick in the level one class when I was learning some proof related to uniform convergence, and then suddenly Professor Kumareshan sir came and then made a comment, introduce a term that helps with the proof. Later, you won't need that term, and then that is curry leaf, and then remove that thing. But ultimately, your proof will be complete. All of you can associate and relate all these things because many times such a deep thing actually in the BSc second year, and this is really very great at that. So moreover, lot of things we can relate the way evening discussions, and then during lunch we had discussions and all those things. So I can't thank enough, but I want to thank Kumareshan sir, Santhanam sir for helping me to discover my true passion. And thank you to all the past and current teachers. I can see uh, Satya, Jai Mehta, Anant Narayan, lot of teachers did so much dedication. So I really thank you, all of you. So I just wanted to say all these things uh, before I start this minimal surface. So now I start the minimal surface thing. About the minimal surface, the what will be the style? Uh,
You can take a 1 hour or so, more than 1 hour, 1 hour, 15 minutes or 20 minutes.
uh, Actually, what my voice is, I'm also listening whatever I say. So I think from my laptop. So I do not know how to fix it. So let me, whether I muted it.
Okay. Yeah, this echo happens sometimes.
Yeah, just a minute. I, so I'm trying, I will put the speaker off, and then if any one of you have comment or want to stop me in between, please just write a message over chat. So I think that will help. And then at that time, I will unmute my laptop.
Yeah.
So,
Okay. Sure. Sure.
okay, so now I have muted the speaker. Now, so what will be the style of today's discussion, or how will we pursue this thing? So the main agenda will be understanding the construction of minimal surface. What is the usual technique one use, or basic stuff we require to construct minimal surfaces? That is the main ingredient of this topic. But before that, what is minimal and what is surface? So let us try to go discuss recall these concepts. So as I am saying, I'll recall these concepts. It will not be focus will be given on the construction of minimal surfaces. So this recall, I will be very quick here. So stop me if you have any problem, or if you have any doubt here. So this is what I have written in the next slide also. So basically, these are the two things. One thing is, what do you mean by surface? Surface sigma in R3 actually. I did not say surface sigma. So I need what I mean is, I will be interested some kind. Just yeah, let me. Yeah. Okay. So now I think this pen is working. So what I'm trying to say is, so surface sigma in R3. So basically, I will be interested a map which takes topological surface to R3. This type of things we will call it a surface in R3. I will define precisely. But what I mean, I'm assuming that all of you know what do you mean by two-dimension oriented. This is the thing I'm assuming. Two-dimension oriented smooth manifold. This is the this I will be assuming. If you do not know this, for the top, you can just feel that M is R2 or open subset of R2. So this you keep in your mind. This keep in your mind, and then everything will be very clear. So the first thing is, I will be, as I said, I will be very quick. And the second thing, here I will focus the construction of minimal surfaces. So then, and then moreover, there are a lot of reference. In the talk, I do not mention any reference in the slides. So then what I'm doing is, I'm writing all the references here. At the last also I will write down. But whatever concept I will be discussing, like minimals, like mean curvature, and like Gaussian curvature, Venn-Garten map, and so these are the two things, two textbooks. Books by, I did not mention which books. Basically, it has Riemannian geometry, differential geometry, so by Jost, and then the few articles by Weber and Wolf, which they have written together during 1997 to 2004. These are the three things you can search, and then you can ask me after the talk to provide the exact content. So anyone wants to learn the minimal surfaces or wants to do something about the minimal surface, so they need to know many books by Jost, like Riemann surface, like Riemann geometry, Riemann surface geometric analysis, something like that. And then pictures, I have taken a lot of pictures from Matthias Weber websites. So the same Weber, Matthias Weber, I will be talking about his few results basically. So these are the main differences. So before now let us start with the surface sigma in R3 and the quick recall. So in the next 4-5 slides, till I define the mean curvature. So basically, I mean that surface sigma in R3. I mean surface sigma in R3 is basically a map from a smooth oriented two-dimension manifold. If it sometimes people you say okay, I will not start from the orientation, that is okay, and other things there are many variations, but for this talk I am fixing myself to this situation. And then what do you mean by immersion? Immersion means this map, differential map is injective, so that is the smooth immersion. So when I say surface sigma, so this is not just a topological object. I have a topological object, and then I have a map also. So this map I am interested actually how to construct this. So basically we are not just interested this object, how this object sits inside in R3. That is the main discussion when we learn the differential when we learn the minimal surface theory. How does this object this object sits inside? So say for example m may be your m may be sphere minus 2 points or something like that. So how does this sits in R3? So that type of things we are interested. So let us fix our mind. What do you mean by surface in R3? This pair. Okay. And now the next thing is we will identify this. What do you mean by identification? See, there is an injective map from TPM to R3. So DXP TP of M. This is 1 1 on 2 1 map. So then we will write down TP of M, and in place of DXP TP of M. In place of DXP TP of M, we will just write down TP of M. So this is the identification we will follow. Whether this identification is required, okay, it creates unnecessary so many things one has to write down again and again. So then this identification help us minimizing the writing. But as a beginner one should not we should be very careful when we say key identification. I feel that this is the most dangerous thing when we say we identified, because in the future we should remember okay, we have identification, then we are doing. For example, just see the next slide. I will go to the next. Just when I say R3 equal to this, so then is just sometimes this then stops. So yeah, R3 equal to this. So this means that this I am identifying as a DXP TP of M, because DXP TP of M is a subset of R3. No? And similarly, this means DXP TP of M per. So we do not write this because this is what, so that is what I said key identification. So let me remove this thing, and then I said that for a surface sigma, we identify this R3 equal to this. Now this makes sense with that identification. You remember now this identification is required. So this is very dangerous if you do not remember the identification. For the beginner, I am saying. Otherwise, if you are mature, then I think this is this one should follow this identification. Now the Gauss map. What is the Gauss map? Gauss map is this is a small n, is a map from N to R3 such that NP belongs to TP of M per. So normal basically. Sometimes you can feel all these things. Again, I say whatever I am doing here, everything you can find out in Presley, and then combinations are Riemann geometry. So then this notation and notation language I just copied from there. I thought I should not. So for example, this slide I just copied from the combination Riemann geometry textbook. So then what does it say? It says that let us try to understand this, right? So it says that take two vector fields in R3. Vector field means y equal to y1, y2, y3 u, right? So this is the notation we use as a derivation. And then this is the differential basically del x nebula xy. Some people say that the connection in R3, and then it turns out that a little very small calculation xpnn is 0, and then xpnn x like this. Xp is a tangent vector, v is a tangent vector, so v of any constant function is 0. So nn is a constant. So then this is 0, and then this will tell you 2 nebula x nn is 0. But then this tells you that nebula x belongs to TP of M. Now you can say that it basically it belongs to DXP of TP of M. So which I am writing as a TP of M. Nebula x belongs to TP of M. But then this so with if you define this as a normal, so and then if you take any x belongs to TP of M, DXP nebula xn belongs to TP of M, and then this allows us to define a map A from TP of M to TP of M. Take any v here, and then corresponding to which you generate a vector field, and then define the minus nebula Vn. And then just now we have proved that this belongs to TP of n. But a little bit analysis of this definition will tell you that this x this whole quantity does not depend just on x, but depends upon the point xp. Basically, I should write which way one write xp. So therefore, this is the reason I said that you take v and then ab equal to minus nebula Vn. And then this is called the Weingarten. And why minus unnecessarily? If you put plus here, then also AB equal to nebula Vn is a Weingarten map. Is a map. But then why minus? There are obvious answer is if you put minus here, many other places there will be many plus in the calculation. But there is a geometric reason also about this. So this is called the Weingarten map, and then some calculation tells you that the Weingarten map is symmetric. And then if it is symmetric, so eigenvalues and real eigenvalue and eigenvector, you know all these things. So eigenvalues are called the principal curvature, and then you take the trace of. This is the mean curvature. Trace of a by 2 basically. We write trace of a by 2. This is the mean curvature, and then Gaussian curvature. So this is the basic differential geometry. I again emphasize because I was quick here for the beginner. If you have never read, then this is little bit difficult. So what I will request you, okay, forget the Presley for now. Read Presley is good actually. Read the Riemannian geometry by Kumaresan sir. What to read? There is a chapter called Gauss theory. Not chapter, section actually. Gauss theory. So after sections and after connection and curvature and after connections, he tried to explain in very easy language actually. So but let me recall what we have done till now. We have defined some object K, determinant of A. So this object we have defined. So and then H and K, and now what is the mean with help of A, you can define a bilinear map. This bilinear map is called, this is the second fundamental form and is denoted by this. And then moreover, suppose and how does it look like if we take the local parameterization? Local parameterization means what? Now listen. Those who know this thing, this seems trivial, but I will very soon come to minimal surface thing. But just wanted to define the mean curvature things and other things. So therefore I'm doing. So X from M to R3 is you are having a minimal surface. You are having a surface in R3 sigma. Remember na? X comma M. And then once you have a surface in R3, we have defined the normal N. N is a map from M to R3. So that this is what normal we have defined. And then once we have defined the normal, we have defined the mean curvature, we have defined the Gaussian curvature. This is what we have done. Now what I'm doing, I'm trying to explain this thing locally. Locally means what? This M is a two-dimensional manifold. What you do? You take some point P and then take a neighborhood, because this is a manifold now. So you will be having a chart phi, which is some subset of R2. And then here you are having map X to R3. You compose it. So X composition phi is a map from some open subset of U, R2 to R3. So so in place of X, when I say let us talk the local version of X. Local means we are talking about this map. This map is some open subset of R2 to R3. So in place of M to R3, you are looking the patches. You are looking the patch by patch. So in the patch by patch, if you write X composition phi, it's just R map. So R of UV, I'm writing as X1 UV, X2 UV, X3 UV. And with help of this R, you can let us try to calculate BRU. So basically, the definition of B is the definition of B is AV comma W. So BRU is basically turns out to be NRU. Here I had minus na, because of this minus we are having plus here. And then this we call in the classical differential geometry, classical notation. This we call as a L. and this is N, this is your M, and then with this LMN, you got this is the classical notation of writing the second fundamental form. This is the classical notation. So what I have done till now, I have quickly recalled it was very quick. Those who are I really apologize, those who have seen who are looking this in first time, but the point is the rest of the slide doesn't is not dependent too much on all these. Why did I define then this thing? Because I wanted to define a minimal surface. So minimal surface are something, those pair x comma m, such that for all p, h is 0. H you can define for p now, for all p. This a was defined for p. Mean curvature is 0. So this is the mathematical condition for what is the minimal surface. Minimal surface is the pair x comma m. Remember here, this is a minimal surface is x may not be embedding, x is a immersion. So it may happen that if you look the image of m via x to R3, it may happen that x of m may have self intersection. X of m may not look like very nice in image. It may be having self intersection, something like that. We do not. So we are allowing the self intersection and other thing when I say minimal surface. So minimal surface is the pair x comma m, so that HP is 0. So and then moreover, I have just explained how does the minimum to calculate the mean curvature. To calculate the mean curvature, what you will do? Mean curvature, I said now, mean curvature is basically h of p. So at the point you calculate the mean curvature. So mean curvature. So this means that around point you can write this capital X map locally. X composition phase R. This way you can write, and then if you can write this. So if there is a local version in calculating the mean curvature, then things becomes easy. So that is what I am trying to do is, and then what I am trying to say is this thing in the isothermal parameterization. If the parameterization is isothermal means what? Again, I will recall. If I was so see, this was the minimal immersion. This was the surface. Surface means the pair x comma m. Okay, this was the surface, and then we have defined the map, this map, R map was some open subset U of R2 to R3. How do you remember what was the R map? R of U comma V was this capital X composition, some chart. There was some chart now. So let's call that chart. So this of U comma V. So this R map. So for the surface, we have given this R map, and with this R map, it turns out that if R satisfies these conditions, this means RU RV equal to RV equal to both are same, and then RU RV equal to 0, then the mean curvature looks very easy. Formula for mean curvature is very easy. And then this formula and other things, where to get? Again, I copied. If you do not understand everything here, because the main aim is construction of minimal immersion. So this basic differential geometry things I just quickly recalled, and then therefore I'm writing it. I copied from either Presley and the accumulation notes. So this formula I needed, because this formula now L I can calculate. How can I calculate L? L equal to N RU. N I can calculate, and then once I am having L, M, and N, and then E also I have. E is this RU RV is E basically, and then it turns out that the mean curvature is 0. Mean curvature is this, and then minimal immersion. What is the minimal surface? Minimal surface is like I told you, minimal surface is this pair x comma m, such that for each p, HP is 0. So HP is 0 means what? For some R which is isothermal. If you can get isothermal, then this is 0. What is why we are interested in this object? I did not discuss yet why so what is the use of this kind of object? This I'm not right now discussing. I'm just discussing what is this. This I already discussed. What is this? Mathematically, pictorially, one can say कि minimal word कहाँ से आ रहा है? And minimal means what? Some kind of area minimizing. So it turns out that this conditions gives you that. So let me make a picture here. What I'm trying to say is कि suppose you are having minimal surface. Suppose you are having minimal surface and you have some point P, and then take a neighborhood, and then take a variation of this surface. Then the minimal surface is the one which is area minimizing. So there is a lot of geometry in this situation, in this condition, and then not just area minimizing. There are many other things. So let us not, because in 1 hour, 1.5 hours, or 1 hour, so we can't touch all the aspects. What we can touch is just a definition that looks kind of rude, not just no feeling right now. Okay, why HP0 gives a lot of good things and blah blah blah. So that I think one can leave for future. One thing one should learn, that HP0 is something important object for XM, and that is minimal surface. And then I want to understand what is complete minimal surface, what is embedded minimal surface, what do you mean by complete in, and what is the higher genus. So this is what I want to understand. And then we want to construct. Can we construct such surfaces? So this is the global property, complete embedded. Here I just made I had just taken pictures from internet. So this minimal surface are this people they are related. This is the people say soap films. So you can see this, so basically this is some kind, this people call it a catenoid. So when you revolve the catenary, you also get the same picture. So what I'm trying to say this is also part of minimal surface. So how to understand the minimal surface for this? So this doesn't stop here basically. So this keeps going on. So this is a part. This is also part of the minimal surface. This kind of object we are interested in. How to construct this kind of object. See, theory was very old, so people were practically it was very clear. Okay, one can get a soap film. One can get a soap film from here. One can get a soap film from here this way. One can get a soap film from this way. But mathematically it is not easy. For example, if I say prove that such surface exists, this means that you want to find out some M. What is that M? You want to find out map R3. And then you want to find a map such that the mean curvature of this thing 0, not at one point. Every point in mean curvature is 0. Here also mean curvature is 0 at every point. And then here this is the G. And then what should be your M? M may be your torus. M may be your sphere. M may be, so what, for example, this looks like a kind of cylinder. And I hope you agree, this looks like kind of cylinder. And then cylinder means you can feel that this is sphere minus 2 point. So here for this surface, you may guess that defining domain may be sphere minus 2 point. Here, what is this? If you think this is a point, a puncture, this is a point, and then there is some kind of hole. So basically, here the defining domain M. Maybe some kind of some kind of Riemann surface, some kind of torus, complex torus. But which complex torus should be the defining domain? It was not easy. I will tell you the difficult main problem actually. See, subject is very old. Lagrange see the year, you just look at this number 1762. He defined the minimal surface equation. Minimal surface equation means what? Suppose you have having map x comma y comma f of xy. This is the map. Suppose this is r of uv. R of uv equal to u comma v comma f of uv. Then what is the equation f should satisfy? So this means that what is the mean curvature 0? Mean curvature 0, you know na, L plus n plus mean curvature 0. There is a formula. So what does this formula tells you about f? That is the minimal surface equation. So this is 1762. So equation was there. So then people were able to find out.
Sir, there is a question.
Which can be written as a x comma y comma f of xy. This means that some graph of some function over R2. graph of some function over R2. I can see one chat. Can I ask a question? Yes, you can ask. Let me unmute. Yes, please.
Hello, am I audible?
Yes, you are audible. Please go ahead.
Sir, can I get the explanation of the cylinder again?
Explanation of?
The cylinder which you showed, right, for the minimal surface.
Sure. Let me repeat.
I don't know whether I am interrupting you. I don't know the rules and regulations. I think I can ask, right?
Yeah,
Okay.
sure. No problem.
So I will now again put the speaker off and then write down whatever you are having in the chat. Let me explain. So again, basically what I want to tell you. The main thing is, let me stop sharing, and then what I do, I will reshare this not just one screen, but sorry, I'll reshare entire screen. So now this is a screen, and now I can quickly go from one. Yes. Okay. So yes. So let me summarize whatever I said. And then explain your doubt also. So what I said? I said that first of all, let me make only pictures. Okay, so picture, when I say pictures, this means some vague, some there will be some vague thing, not very precise, but whenever you are having some kind of doubt, okay. So you are having, this is your M. So and then minimal surface means what? X M to R3. So then the image may be something like this in R3. Image may be something like this. So and then mean curvature. So mean
Sir,
mean
this means
curvature is
we are
0. At every
projecting it.
point mean curvature is 0. So see, you can think this point somewhere here also via X map. So mean curvature is 0 at each and every point. So this kind of object we want to construct. Now how to construct this kind of? First of all, one have seen that very popular example. People may have you have seen this kind of object, catenoid. So sorry, this is not a very symmetric one. So you understood what I mean. I'm not good at. So catenoid. So catenoid means what? This I assume that you know this object, like this surface you get by the rotation. You rotate around. You rotate a catenary, so you get a catenoid, or this. So something this kind of object you got. Now one can prove that that minimum that surface of revolution turns out to be everywhere mean curvature is 0. So it is a minimal surface. But in our setting, if I want a minimal surface like M to R3, so this means that what I want M is a two-dimensional manifold. Two-dimensional manifold. This means that what is two-dimensional oriented manifold? What is the choice for M? Two-dimensional oriented manifold. Either it will be sphere, or it will be torus, or it will be higher torus. So these are the only topologically. These are the only possibility for topologically only possibility for this M. Here, what should be my M? It looks like that. This is cylinder minus 2 points. Cylinder minus 2 points. So suppose if M I or I should not say cylinder minus 2 points, sphere minus 2 points. If I, for example, if I take this north pole and south pole, if I take this sphere, and somehow I define a map X. Such that this thing blows like this. This thing, as soon as you go here, this thing blows. It will keep going, and then this thing is also blows, and then you get this type of picture. So this may be one of the possible candidate to define the catenoid, to define some nice map X for this kind of object. So similarly, we are, and then if M is of in this case, M kya hai? M is sphere. Sphere means it is a genus 0. So we say that it is a genus 0 minimal surface. It is a genus 0 minimal surface. Is it? We are projecting it into another dimension. We are writing. We are, yes, we are looking this object M in R3. Inside R3, we are doing everything. These pictures basically. These pictures we are looking in R3. But what? Which in your sense you are saying projecting? No. What is the good way to say? Immersing. You know, some you have a water and you have a pencil, and as soon as you immerse, it will be it will be tilted, a little bit tilted, not the straight line. So you are immersing, and then you are looking this kind of object. So immerse, you are looking immersed picture, immersed thing, and then so after immersion, what is happening? Whether it becomes mean curvature 0. Mean curvature 0 in some sense you can feel that everywhere saddle point is saddle point. Everywhere point is saddle. Every point is saddle point. So this is the mean curvature 0 condition basically. Mean curvature means what? Your mean curvature means just now you got. I got a question. What is the mean curvature? So I have defined the mathematically mean curvature. Now this is the mean curvature. I have defined the mean curvature. Let me explain the mean curvature picture intuitively. So intuitively, something like that. What you do? Therefore, it is intuitive. Intuitive means there may be a little bit now looseness when I say. Mathematically, I have already defined, and then I can share this slide with you. You can check what is the mean curvature. This is the mean curvature. Okay. So what you do? What is the mean curvature? Suppose you are having this point. You look, all the curve passes through this point. You see all the curve passes through this point. Okay. Yes. And now every curve, you find out the curvature. There is something called the normal curvature. Find out the normal curvature. Normal curvature at least tells you that how does it bends in that along that curve. How does the surface bends along that curve in some sense. So now find out the normal curvature. Take two. Suppose at this point one curve is this, and then other curve is this way. Let us say. So find out the so it has some curvature. In normal curvature, this curve also has some normal curvature. Somehow find out the curve which has maximum normal and minimum normal curvature. Whether you have so many curves, whether this type of curve exists and all those things, there are a lot of questions. Suppose you are able to find out. So then those directions, those curves are called the direction of those curves are called the principal directions. And then curvature of those curves, let me call K1 and K2. These are called the principal curvature. And then average of this principal curvature is basically average of this thing is the mean curvature. So what is the mean curvature? Mean curvature is this K1 plus K2. So average of this. So when I say 0, so this means that K1 equal to minus K2. So this means that there will be one curve whose curvature is normal curvature is positive. There will be another curve whose normal curvature is negative. So this means that everywhere you are having equally saddle thing. So something like that. Can curve passes in in any other way without mean curvature? Okay. And then, anyway, so now coming back to this construction part. So then I am interested. I'm interested highly. Now, pardon me for this very means it's not very mathematically, just intuitive, because some feeling is really important in the beginning. We are all MPTS students. So first, as soon as we are having feeling, we can write all the mathematical jargon and nonsense. This is the mathematical jargon, mathematical thing. I just wanted to be very precise. So therefore, I thought let me write and define it. But now I think I should tell intuitively. I'm interested in highly this saddle. So I'm interested in an object. So object means the picture in R3 I'm taking, such that every point you are having is a saddle point. One curve is this and another curve is this basically. Every point is a saddle. Every point is a saddle. Not just every point is a saddle. Equal and opposite saddle in some sense. That is that kind of object I am interested. Equal and opposite. It is not so object we are interested in. Now, so I just tell you the problem. Actually, it was not very easy problem in the beginning, and then then it turns out that up to 76, we were able to check that helicoid and catenoids. These are the only examples, and we had no examples. We had no examples long. See, 1776 and now almost 100 year now. No theory, no examples. And then, but then Versta's representation, which we are going to discuss today, he has related with minimal surface with the complex analytic. So that I'm going to discuss a little bit, touch of the Tychomer theory with the minimal surface. So that I'm going to, but anyway, so this is but 1866, but no example. Let us go to the 20th century. What happened? See, 1770. See these years. Osherman is the Osherman is the person who discussed global behavior of minimal surface. Means what do you mean by genus zero minimal surface? Genus zero, like I have defined X from M to R3, and so the genus of M is called the genus of the minimal surface, and all those things he developed, he formulated a lot of nice theorems. But again, see, no examples. No examples. If I ask you, does there exist a genus 1 minimal surface? Genus 1 means what? This is the genus 1, but every point I want a saddle. But in usual torus, do you have every point saddle? No. But can we somehow deform it? Like one of you said, na, project it. Can we somehow deform it in R3? Such that we get some kind of every point saddle, but it has some kind of genus. Do we have such examples? People were interested, and then people thought till 20th century, 1976, people thought that no, there are no such examples. And then only examples are helicoid and catenoids. So 100 years here and almost 100 years here. So, but then what happens? Miracle. The theory of minimal surface, it was defined so many years, 1762, but real theory started in 1983. It is the breakthrough time. And then Costa discovers a new minimal surface of genus 1 and 3 embedded planarine. I will define what do you mean by embedded planarine. So this is the picture of the Costa surface. I will show you. This is the picture of the Costa surface. This is the genus 1, 3 end, 1 end and 2 end, and the third end. What is the end precisely? I will explain. But so via soap film it was there, but mathematically how to prove that such surface exists? It is not easy task. And then but this was the Costa who developed, and then George Meeks has developed classified. Once you have a Costa, so these techniques one can extend a lot. And then George Meeks has extended and then did everything related to whatever you can do. Everything means okay, some people may come and then they can give a new thing out of Costa. But the point is, lot of things George Meeks has classified examples. And then the Hoffman Meeks, it's the same Meeks. Develop the key result. What do you mean by properness, embeddedness? Like I said, generalizing the Costa. Where are we nowadays? Modern development. Curvature in 2000 Curvature extended the family and has given some, but the method was this. All the method was the Costa surface method. Costa surface method. Basically, this method I can see I should not say Costa surface method. The method is basically people give credit to Meeks and then Hermann Krecher. These people have given a method, and then that method help us to expand the family and all those things. Right now, we are doing right now a lot of examples we are having, but still some developments are going on, and some, like you can see now, like 1776, only there are but only available techniques are very few. So can we develop a new technique and then all those things? These are the major problem in this area, and so that we can solve the open problem. Means there are very easy equations are still left there, but those are very hard. Hard means you can see, because people have thought a lot from almost 300 years back. So it is so what we are going to do? we are going to touch some of the aspects of Wolf and Weber theory, and then of course starting with Osserman. So then for that, the base, I will be needing little bit Riemann's surface complex analysis, and then I will show you how to construct one surface. But before that, let us try to build a background again. This is the, like I said, this is the main agenda. Aim of the remaining talk I have written. How do we construct the minimal immersion with the required property? So these are the keywords in the remaining talk we will learn. Minimal immersion is harmonic map. Minimal immersion actually turns out to be harmonic map. And then relation with the complex analysis we will see. What do you mean by complete minimal immersion? That we will see. And then various method of constructing minimal surface. That we will be doing in the remaining talk. So starting with the minimal immersion is a harmonic map. So then I will come back to this mathematics expression again. So this was the mean curvature, h equal to L plus n divided by 2e, and then I will just share this screen with this slide with you, or you can take a maybe screenshot also with some calculation. It turns out that this some calculation means what? This is the calculation and very easy calculation. It turns out that if R, what is written here, I will just write down in one line. Suppose R from some omega subset of R2 to R3. And what was R? R of u comma v equal to x of uv, x1 of uv, comma x2 of uv, comma x3 of uv. Then if mean curvature is 0, and then moreover, R is an isothermal parameter. R is an isothermal parameter. And then if mean curvature is 0, then what turns out to be delta R equal to 0. What I will repeat, this is very important fact. I will repeat again here because I do not know whether I was able to explain clearly or not. What I'm saying is R from sigma, R from omega subset of R2 to R3. Suppose this is a minimal immersion. This is a minimal immersion. Sometimes this is a minimal immersion. Sometimes people say like this. Sometimes people say like this. R comma omega. Sorry. R comma omega is a minimal surface. Sometimes people say like this. Minimal surface. This the same language. Na x from, in place of x. Now I am saying x R from M to R3. So x comma m na, x comma m. Suppose this is a minimal surface such that parameter is isothermal. Parameter is isothermal. So suppose this is the setup. This is the setup means what? पहले setup समझते हैं. What is the setup? Setup means what? So setup is this. You are having R2 and you are having, this is your omega, and then this is your R. And then R is basically R is x1 R1 can write as a x1 x2 x3 x1 x2 x3. This is your R. Now you take some point here, and then suppose you take two curves, and here also you are having corresponding to R take this curve. Suppose you are taking this curve here and this curve here. So angle preserve in some sense. Angle preserves. So that I mean is isothermal. Conformal one say, but here the parameter are open to R2 to R3. So we use the word isothermal. So isothermal parameters are isothermal. So this is the setup. Setup is clear. It is not random map. It is a map which preserves the angle, and moreover, it is a minimal immersion. Then it turns out that R of uu, partial derivative of R with respect to u2 times plus RVV. Sometimes we denote this is a triangle R. This is 0. It turns out this is 0. This means what? This is what I have written here. Sigma is minimal, means x comma is minimal. If Laplacian is if it is harmonic. If delta R is 0, delta R means what? R of uu plus R of VV 0. R of uu means what? X1 of uu plus X1 of VV, comma X2 of uu plus x2 of VB, comma, x3 of UU plus x3 of VB, that is equal to 0. So this is the vector notation. When I say it is 0, it is these three things 0. This means that each of these xi's, each of these xi's are harmonic map. Each of these xi's are harmonic map. So this is the very path breaking in the theory of minimal surfaces. Geometric thing, minimal curvature means saddle point. You are relating with the complex analysis, harmonic or complex analysis, and then it helps us that stretch a little bit more. Stretch a little bit more means what? You define. See, R क्या था? R क्या था तुम्हारे पास? R was x1 UV, comma x2 UV. I am writing this thing again and again, but now let remember this thing. R equal to x1, x2, x3. Now define this phi j. Phi j is mapped from where to where? Phi j is mapped from omega to complex plane. This is the phi j map. Omega is a subset of C. Now I am identifying omega like u plus u and v ko I will write down u plus iv. So omega is a subset of C, and then phi j is a map from omega to C, and then phi j. This is the way I define. This is the my phi j. This definition makes sense. Del xj by del u, del xj by del v makes sense. So I am defining phi 1, phi 2, and phi 3. And after defining phi 1, phi 2, phi 3, what do you get? It turns out that if I calculate, if I solve situation, it turns out that this phi j square, this is the calculation. If phi j given hai, you just calculate phi j square and then do all these things, and mod of phi j square is this. And with this understanding, now listen. Suppose if I say phi j square is 0, so this means what? This equal to this, and this is imaginary now, and this is equal to 0. So this is equal to 0 means what? This is equal to this, and this is equal to this means what? And this equal to 0 means what? This means R is isothermal. R is isothermal. So what I'm trying to say is we have written very nice expression. Suppose you are having a minimal immersion. Locally, you can write minimal immersion as this with locally with isothermal. So this is also result. You have a minimal immersion. You can always find R, which is isothermal locally, and then so that is what I have written. Obtain the isothermal parameterization R, and then define phi j. And with this phi j, it turns out that phi j square is 0. This condition, this is same as saying that RU RV equal to RV. ये calculation है. This is n, and RU RV is 0. Both are same, and this is equal to 0. This implies this is 0. And then moreover, we have seen that it is minimal, and parameter is isothermal, so phi j's are holomorphic. And then this is this condition is actually is also required. It happens because this condition is equivalent to it is a immersion. Actually, it is a immersion. And moreover, if you take integration of phi j, it turns out that all these things happen. See, all these things one can't verify in this discussion. So how do you pursue this thing right now? If you have seen this, looking at the first time, you feel this slide such that okay, if you are having minimal immersion, this means that I can find some phi j map such that this is 0, such that these are harmonic, holomorphic, such that this is greater than 0, and such that integration of phi j over any closed loop on omega is purely imaginary. You can find this. And then moreover, xj I can write as this. This is not a many things we have proved in the previous slide. You may not realize right now if you are looking this thing first time, but then this help us a lot. That if you are having minimal immersion, you can get phi j. I will explain in a copy again because this is very important. I request raise your doubt if you are having in what I'm going to write down. What I'm going to write down, suppose you are having X map from M to R3. Okay, this is the, suppose if I say it is a minimal. Minimal means geometric thing. This means what? Mean curvature is 0. Suppose if I say minimal. So via this, what you do? You find out a isothermal parameters. Can you always find? Yes, you can always find. Is there any result? Where you can find? Again, in the reference, I can share the main reference, all these things. And then with help of this, if you are having isothermal parameterization, then with help of this, it turns out that locally I am writing Laplacian of capital X is 0. Not see X from M to R3. Now this means what I'm saying. If you are not able to understand this one, you can just in place of M ki jagah, you just replace M to U subset R to R. And then so now it makes sense to you. Now, Laplacian of X is 0. Laplacian of X is 0 means Laplacian of X1 is 0, Laplacian of X2 0, Laplacian of X3 0. And moreover, it turns out that we have defined 3 functions, phi1, phi2, phi3. These 3 things. These 3 things, where did we define? These 3 things we have defined, phi1, phi I we have defined from some, again, this U I am identifying as a complex plane, U2 complex plane. This is phi I we have defined. And then this the nebula X is 0 implies phi I is holomorphic. So given X, I can find phi I. So summary, let me say summary. Given X minimal, we can find phi j such that X, suppose X is my X1, X2, X3, such that Xj equal to integration over, what was Xj? Xj was integration over Z0 to Z of phi j, the real part. So this is your Xj. So this is the very, very important line. Given X, which is minimal, this means that X from M to R3, you can find phi j such that Xj turns out to be this. Other way. This was the major breakthrough in what? In whether are we able to construct the minimal immersions? So this gives a method one can ask. Suppose you are having U subset of R2. So let me take, if you agree, let me take U equal to complex plane. Okay, complex plane minus 0. Let me take this for the I just want to explain something here. So C minus 0. Otherwise, I would have taken C here. And then I start with 3 holomorphic function, phi 1, phi 2, phi 3. I start 3 holomorphic function. Let me say phi 1 is holomorphic. Let me take phi 1 equal to 1 by Z. Phi 2 equal to Z. Phi 1 Z is holomorphic or not? Yes, it is holomorphic on C minus 0. Yes, phi 2 is holomorphic. Phi 3 Z is square. These are 3 holomorphic functions. And now I can ask, let me write down dz also. So these are holomorphic form. People say in complex analysis, these are holomorphic form, holomorphic one form. And now with this holomorphic one form, I can ask, what is integration? Whether if I define, I can ask now, if I define x1z equal to real part of z0 to z, 1 by z dz, and x2 comma x2z if I define equal to real part of z0 to z, 1 by z dz, and similarly x3z is phi 3. So with this x1 x2 x3, I can ask whether capital X is a map. I am defining capital X is a map, U subset R2 to R3, and the map is given by capital X of Z equal to x1z comma x2z comma x3z. I can ask whether this thing is a minimal surface. See, look at the claim. What I'm saying? I am saying that you start with a 3 holomorphic function form. three holomorphic form on this domain, and then define x1, x2, x3, and then I can ask whether this is a minimal immersion or not. Look at this. What was that? If you have x1, x2, x3, you get phi j, you get xj, and then then it turns out that these are minimal immersion. Other way can you do? Other way can you do? So this, so then that is called the yes. If some condition satisfies. If some condition satisfies. What is that condition? Condition is same. If you start with 3 phi 1 phi 1 phi 1 phi 2 phi 3. Remember, these are 3 1 form. These are 3 1 form, such that this is 0, such that these are holomorphic, such that this is greater than 0. And moreover, this line, if you do not understand this line, it means that such that if integration makes sense, because see, integration, you are integrating z naught to zeta, Suppose z naught is this point, sorry, zeta naught is this point, and zeta is this. So integration zeta naught to zeta means there are many paths. So integration, to make sense, integration is well defined. I have written this thing basically. So if phi 1, phi 2, phi 3 are such that this holds, and this holds, then you can, whatever you will get, that you will get as a minimal immersion. This is very, very important thing. Very, very important thing. And then phi 1, phi 2, phi 3. What are phi 1, phi 2, phi 3? Phi 1, phi 2, phi 3 are 3 1 form. 3 1 form means some holomorphic function into dz. And then what you do? You little bit change it. And then write down this way. What you do, if you do not understand what is written here in this line after applying and all these things, I just give you quick idea, because I think too much mathematics. So what I'm saying is, this is your phi 1, this is your phi 2, this is your phi 3. So what is phi 1? Phi 1 is this into dh. Phi 2 is this into dh, and phi 3 is dh. So given phi 1, phi 2, phi 3, if integration is well defined, you will get this. You will get minimal immersion. But these phi 1, phi 2, phi 3 should satisfy this condition. What I have written is, if in place of phi 1, phi 2, phi 3, in place of phi 1, phi 2, phi 3, in place of phi 1, phi 2, phi 3, in place of phi 1, phi 2, phi 3, you just write down a meromorphic function. G is meromorphic function, and dh is holomorphic form. dh is holomorphic form. People do not confuse this thing with a closed something. This is the notation we use here for just holomorphic form. Do not omega dh. So if you are having a meromorphic function in holomorphic form, and then you write phi 1 as this, phi 2 as this, phi 3 as this, then it turns out that this will satisfy this condition automatically. And then with some required g and h, these two conditions can also be satisfied, and then this gives you minimal immersion. So this is called the famous Weierstrass-Enneper representation. I'm sorry if I'm too fast or too slow, because I do not know what should be the required speed. But I will be happy if you after this talk, at least if you are new, if you have seen this thing first, looking this thing first time. So if you understand this Weierstrass-Enneper representation, then I think we got enough. So I will be happy. So the point is, what is the Weierstrass-Enneper representation? I'm explaining. I'm writing something else to explain Weierstrass-Enneper representation. So how to get minimal surface? Now we understood how to get minimal surface. Why a Weierstrass-Enneper representation? What is Weierstrass-Enneper representation? You start with a Riemann surface. Step 1. What is the step 1? Step 1 method samajhna. Step 1, you start with a Riemann surface. What is the Riemann surface? Sphere, and then sphere with some complex structure, and then lot of torus, and then torus, lot of torus. I will make torus as this torus, and then, because see, there are a lot of Riemann surface structure on torus. So there are a lot of Riemann surface structure on torus. First step is find out a Riemann surface. That I will call as a map. Riemann surface. And then second step. What is the second step? Step 2. Second step is find out a meromorphic function, capital G. Capital G. What is capital G? Meromorphic function. Meromorphic function. Where? On Riemann sphere. Sorry. I'm not saying Riemann sphere. Riemann surface. Riemann surface are something look like complex plane or anyway. So find out a meromorphic function on Riemann surface, and then find out a holomorphic form. So these are the two things you find out, such that some condition satisfy. Condition. What is that condition? Some geometry will tell you. Suppose I say I want a minimal immersion, such that something happens. So that something will tell you what condition I need. So suppose if you are having these two things, then you are done. Then you are done means what? But not random, such that integration G inverse, such that integration makes sense. Then you can get a minimal immersion. Very good. You can get a minimal immersion. So let us do a very simple problem. Find out a minimal surface. अब कंडीशन क्या है? नंबर 1, condition such that it has a genus 0. Number 1. Number 2, what is the next condition? Such that it has a two end. Two end means what? So I already explained you are having defining domain with two puncture. So find out a minimal surface. Let us try to find out a minimal surface. I will write down next line, then it will be very clear to you. Find out a minimal surface, genus 0 and 2 end. Remember this thing, and now I let me scroll. So this thing is clear now. Find out a minimal surface, genus 0 and 2 end. Okay. So I want a genus 0. So what is the genus 0 minimal? Genus 0. So step one is I want a Riemann surface. So Riemann surface, it is very clear, like C minus 0. This is the Riemann surface. So this Riemann surface is a genus 0, and has a two puncture. What are the two puncture? One is 0, another is infinity. These are the two puncture. So now I to get a minimal surface, I need G and I need omega. Omega in the literature, when you read Weber and Wolf, so they write is a DH, but DH is little bit confusing. You may feel it is closed form. No, it is just an omega. I need one form. Meromorphic function. So can you give him one meromorphic function on C minus 0? Yes, of course, you can give a lot of meromorphic function. Can I write down GZ equal to 1? This is the simplest example. Of course, one can write GZ equal to 1, meromorphic function. Can you give me one holomorphic function omega? Yes, 1 DZ. So whether it will give a minimal surface? Yes, it will give a minimal surface. Let us try to find out minimal surface. What is that? Xz equal to real part of integration. I do not remember the formula for G inverse minus G. What is G? G was 1 now. So G was 1. I take G is 1. So then this will be 0, 0. And then this is the DH. DH is, what is DH? Sorry, what is DH? Oh, where is that? It is here. It's here. What is DH? DH is 1 DZ. So then XZ will be very easy. XZ will be just a real part of integration 0, comma, real part of integration 0 DZ, 0 DZ, comma, real part of integration DZ. So that's it. So what is XZ? XZ is 0 DZ means 0 plus constant you can put. And then because it depends upon the integration of the path. So I can put that constant 0 also. So 0, 0, and then this will be what? Whether this is, so this is the minimal immersion. This is the minimal immersion. Whether now this is very good. So we got a minimal immersion, both simple, very. So what is the difficulty now because now it is very easy. Let me explain the difficulty. Whether this thing is a minimal immersion on C minus 0, let us try to see. So what is this C minus 0? So C minus 0 is basically you do not have point here. And then infinity is also not having with you. Now this is little bit difficult, which are not difficult. Those who know Riemannian geometry, they can understand easily. But for the first time, if you're a MSc student or so, all these things may be very difficult. So what I'm trying to say is, see, as soon as what you do, you take a path which goes to 0. Can you write down the limit of xz? So what is the image of what is the minimal immersion? How does the image look like? Image look like 0, 0. Sorry. I made mistake here. Real part of z. Real part of z means x. So x comma y will be. So how does the image look like? 0, 0 x means yz 0, 0 x. So what is that? What is this? Y x is 0 always. Y 0 always. X varies. So the image is basically x varies. So if it is x axis, it is y axis. This is z axis. X varies. X is 0, x 0, and something this plane now. This plane. So this is the plane. Now in this plane, if you take a curve here, this point is not in the domain because I want a minimal immersion defined on C minus 0. Here I take this curve. This curve is somewhere image is this, but this curve is here. This point is not there, but in the plane, if you take any curve which also pass through this point, which also go to this point, length of any curve will be finite only. Length of starting from this point, length of any curve which approaches to this will be finite, but this point is not there. This type of situation we call is a incomplete. This is not a complete minimal immersion. This is not a complete minimal immersion is what? If this point is not there and you are approaching to this point, so corresponding point here, it should also be not here in some sense. So what I'm trying to say is, it is very mathematically, it is very easy to say that divergent path, the length of the divergent path is infinite. So then we say that it is a minimal immersion is a complete minimal immersion. So though we got something, but we did not get a complete minimal immersion. So let us come back to this thing. As soon as you put condition is complete minimal immersion, embedded minimal immersion. So then finding G and DH turns out to be very difficult. Finding G and DH looks very easy sometimes, how to find out G and DH. But if I say you find out all the meromorphic function on the complex plane. Suppose defining domain is this. Find out all the meromorphic function. You can find all the meromorphic function. How does it look like? Rational function. I said find all the meromorphic form on the complex plane. You can easily find out. You can write an exact expression. But if I say that if you are having higher genus surface, Riemann surface, and find out one meromorphic function here, and find out one holomorphic form. So then think such that it should not be random. It should be some geometry things should also hold. Okay, it goes to 0 and all those things. So then I think then it becomes a task of handling. So then you need a little bit bigger theorems. And then moreover the problem moreover which Riemann surface structure you should put to find out the right meromorphic functions and right holomorphic one form. So Riemann-Roch theorem and then Serre-Duval. You need a lot of complex analysis to understand the existence of meromorphic functions and holomorphic one required holomorphic meromorphic functions and required holomorphic one. And second difficulty is basically you want that integration. You want integration is well defined. Integration z of this thing is 0. So what is the guarantee that integration is well defined? This is basically this thing. This is basically this. You want g and omega such that g omega equal to 1 by g of omega bar. You want this and you want this type of g and omega you want. Now it puts a lot of restriction. and no theory has been developed which classify all the G and W such that this happens, and all the geometry in the complex in the type in the Riemann surface or in other mathematical content. So then every time such G and W finding becomes a difficult task. But without this you can't without this you can't find. It is already 3:20, so I will just show you some pictures. Some pictures one can how, what is one interested, one people are interested, really interested, is G and omega, such that integration G omega equal to integration G omega 1 G inverse omega bar for every homology basis, for every gamma. Gamma is what? All the homology basis. All the homology basis means what? Let me explain a little bit. So you want you take all the curve. You take all the curve. To make integration well defined, you need not for all the closed curve integration should be 0. So something like that you need. So that is what this condition actually. That is what this condition. That is what this condition I have mentioned, that integration GW equal to gamma and what is this gamma? Gamma is all the closed curve. And then if I want this I will say that genus 0 minimal surface with 1 2 3 4 5 6 puncture. One can ask a lot of questions. This is your famous catenoid. What is the Weierstrass data for catenoid? Weierstrass data you can write down GZ equal to Z and omega equal to 1 by Z dz. And then it turns out that it is a complete, it is a complete embedded minimal immersion with 2 punctures. If one wants to understand what is the completeness means that pullback metric is complete. This is the pullback metric on M. This pullback metric is complete. So then this is your popular catenoid. This is your popular helicoid, and then Weierstrass data for this thing is again you can write down GZ equal to Z and DH equal to 1 by I by Z dz. GZ equal to Z and DH equal to I by Z dz. So something like that. And then this is called the inner surface. Here also one can write down the Weierstrass data. A lot of pictures I made, and then I thought that I will explain a classical very nice technique to explain you how to find out the recent examples of the minimal surface, how people find out the recent example of the minimal surface. For that I just how one can get a Riemann surface, and then after Riemann surface how can one get a required one form, and then required one form you will get a flat metric with cone singularities, and then how does those cone singularities help us to find out the minimal immersions, classical Teichner space theory, and then how can you get the conformal map, and then all those things are here. So whatever these slides are there, I will just explain. I will just take you only 2 minutes or 3 minutes to explain recent. Not of course I can't explain everything, but I'll just explain how recently people are approaching. I want G omega equal to G inverse omega for all gamma. This I want. I want a Riemann surface such that in a meromorphic function and meromorphic form, holomorphic form and meromorphic function, such that this happens. So for that, what this means, what? Suppose integration of this thing is equal to this complex number denoted by this line. So integration of this should be something like this bar, this bar. So then people thought that okay, with help of this type of pictures, if I get a one form such that period turns out, these are called the period turns out to be this, and then for this period turns out to be this. So lot of techniques people uses, and then ultimately they try to find out G and DH and on a Riemann surface M, and then but the main problem actually but then all these techniques, there are in the literature there are only 4 techniques available from starting from 70, 76 or something. 4 techniques available. One is PD method, like I told you, key F satisfies some equation. Second is mix. I told you mix. Third is Weber and Wolf, which I was trying to explain. And fourth is I do not have time even to touch that thing. That is the Martin Trajet. These 4 techniques are only 4 techniques are available to construct minimal surface. So, and then all the techniques has a limitations, and all these uses heavy Teichmüller space theory. This uses a lot of Teichmüller theory, and then algebraic geometry techniques. So these are quite old. So this uses just a Riemann surface and Riemann rock theorem and all those things. This is very old. So this uses the variational technique, PD and all those variations. So this but then can we really construct can we really generate, can we really create new methods so which can maybe solve many conjectures? Because see, though subject is very old, but still there are very few surfaces we are having with us. For example, let me explain. Let me tell you one thing. Now, see, if I ask you, this is a famous Costa surface, and then I thought that I will explain the Costa surface also. But anyway, moving ahead, this is the surface of genus Inepar surface and the catenoid end. One is Inepar end, another is catenoid end. People asked this question: can you add a gene handle here? See, so this is a Inepar surface. Sorry, this is a catenoid end. This is a Inepar end with one genus. And then for this surface, people found what is Riemann surface. Riemann surface should be a genus one, of course, genus one Riemann surface with 2 punctures, and then some Weierstrass data and some DH and all those things. This is the only method, no? This is the only method. Method seems very easy, but the finding turns out to be difficult. And then the people thought, okay, you are having one genus. What about this? What about this? Answer is we do not know. No, I will not say no. I say in Weber numerical via numerical techniques. There are numerical techniques also. People conjecture that this object might be there. One can prove that this exists, but we do not know the proof. We are trying the proof. One of my students is trying the proof of this one. So can we proof of this thing is given, but you can't easily generalize the proof of this. And then this requires a real algebraic geometry and complex analytic techniques. So I will just at the last I will just share you the status this picture with this thing with you. This website is minimal surfaces.blog. This website is Weber, created by Weber. He tells you that what are the surfaces till now we are having. For example, if I am interested in triply periodic minimal surface, so these are the only surfaces we are having till now in the genus 3. Genus 4, we are having these. Genus 5, we are having this. What about higher genus? Genus 6, genus 7, we are having these. Genus 9, we are having this. Genus 13, we are having this. So on. But so long back in 1976, around 1950 or 1976. But we do not know other genus and or general theory. Do we know? We do not know general theory. So so this website creates a lot of. He has created a lot of pictures. Put a lot of effort. Look at this picture. This is called the Schwarz P surface. Schwarz B surface. The existence is given by mix. And then you can see the hyperbolic, and then anyway, we could not touch that complex analysis and Riemann surface and all those theory. But the point, how to generate these pictures? Mathematica code. He has shared the Mathematica code in public. One can use all these things and Boreals. But point is this subject is still not too many things we know. Lot of open problems are there. Lot of but the point is, I can say difficult problems are left. So it is not easy to handle this situation, because see, easy things, 70 76 people have already developed, and then we are using Weber and Wolf technique. So I will go to the first slide. So we Weber, Wolf, Martin, Trejet. These are the techniques we are using. So can we develop new technique? Where did I write the technique? I think I have written the technique here. Yeah. So we are using only these techniques. So we are trying, I am trying, can we develop some method of, so basically one project is flat metric. Do you know flat metric basically? So see, gdh is one form. Every one form gives you flat metric with the conical singularity. So gdh gives you on a Riemann surface, gdx gives you a flat metric. G inverse dh also gives you a flat metric. How does these flat metric interacts? And then going to some space of flat matrix, can we play some game there and use the dynamics of Teichmann theory to tell how does these two one form should be to get the required minimal surface? Does it make sense? If it doesn't make sense, it's okay. Only outcome only outcome of this talk is I think you should know what is the definition. If you are first time learning this thing, you are what is the definition of the minimal surface, and then the way I have defined. I have defined XM type. The second thing is how did we get the Laplacian x is 0? That is very important. Third thing is how did we get the Verstappen representation, G inverse DH and GDH business. Basically, xj equal to integration phi j real part of this. How did we get this thing? Because this tells you method. So and then fourth thing is okay, there are in the literature there are some methods already available. And then if you are interested in learning this content, for that the basic basic up to at least you should know what is the Teichmann spaces, Teichmann theory, and then a little bit hyperbolic geometry. So because see a little bit of this flat metric, Maria Mirza Khani, and then all those people, you know. So how does the geodesics on that flat metric and other things? But anyway, count. So whether that can help us or not. So all these basic things you require in the complex analysis to understand. If you want to give some if you want to solve some real problem, because the problem here is a little bit difficult. So yeah, I will stop here. Sorry if I took so much time. I do not know how much you understand. So yeah, thanks.
Thank you, sir. It was really enlightening. So, if anybody has any question, kindly raise your hand or text in the chat box. For those watching on YouTube, you can post your questions in the comment section. We'll make sure that the question will reach the speaker. I think there are no questions, so maybe we can go for a group photo now. I request everybody to turn your cameras on, so I'll, we'll have a group photo. Can everybody please turn their cameras on? Okay. The rules are simple. I'll count up till 3, and on 3, I'll click a photo. Okay. So 1, 2, and 3. Yeah. Thank you so much. Thank you so much. So, sir, it was really good. It was, I didn't feel like a formal talk. You were so good. It felt really nice. I thank you a lot for, coming on a Sunday afternoon, that were 2 p.m. and, helping us a lot. I also thank MTTS Stress, Soumya sir, and the entire organizing team. So there will be there will be another talk at 5 p.m. So the same link is, where you have to come. So yeah, you
Very
can log out. Yeah.